We'll be doing Module 11 Inferences involving population proportions. I know you guys are getting a little bit fatigued with all of the inferential statistics that we're doing because it's sort of similar over and over again. And so this is really our last sort of inference type of calculation that we're going to learn, and then we're going to move on to chi-square, so you'll get a little bit of a breath of fresh air with something new. So what are we doing in this module? We are going to try to understand what a population proportion is and how it differs from a population mean. We're going to identify and use appropriate notation and terminology for proportion-based inferences, and of course construct and interpret both the confidence intervals and the hypothesis test for one and two population proportions. Here's something that's surprisingly interesting about inferences for population proportion. So they don't actually depend on the population size most of the time. When you're using a population proportion, like the proportion of people, for example, who support a policy or do a vote, the accuracy of your estimate mostly will depend on your sample size, but also the variability in the proportion and how close that is to 0.5 rather than how big the population is. So whether you're sampling 1,000 people from a city or 50,000 or 1,000 people from a country that has 50 million, your confidence interval for the proportion will almost always be the same. And this is really cool because it means you can make reliable inferences about huge populations without needing huge samples. And that's why national polls often use samples of only 1,000 to 2,000 people, and they report their margin of errors. So statisticians often need to determine the proportion of a population that has a specified attribute. And some examples of that would be like the percentage of adults that have health insurance or the percentage of cars that are imports. And in this example here, you can see that the CBC surveyed over 1,000 adult Albertans, 747 are male and 434 are women. And they wanted to look at these to decide whether the percentage of men that vote for the NDP party or the New Democratic Party is smaller than the percentage of women who vote for the NDP. And this kind of thing is very important when we start to think about policy and we think about administration. And for a lot of you guys that are going into the healthcare field, this is going to become very important when we're talking about your wages, because everything that your union works with is with the government because it's a public service. So what we have will be two populations and one specified attribute. And the problem is to compare the proportion of one population that has that specified attribute to the proportion of the other population that has that specified attribute. And we'll look at some definitions for population proportion and sample proportion. So consider a population in which each member either has or does not have some specified attribute. Then we'll use the following notation and terminology. The population proportion, P, so you can see that we're going to be using this symbol P, is the proportion or percentage of the entire population that has the specified attribute. The sample proportion, on the other hand, is going to be called P hat. So we've got a little P and we've got this little triangle hat over top. And the proportion or percentage of a sample from the population that has the specified attribute is the definition for your sample proportion. So what you really have to take away from here is the symbols. If it's just the P, it's a population, and if it's got a little hat on it, that's your sample. And this comes back to probabilities, which we did really early on in this in the modules. But don't worry, you don't have to go back and recall a ton from that. All we need to know is that the properties of the binomial experiment. So to calculate p hat, and again, this I don't think is on your formula card, so feel free to write it down. But p hat is going to be equal to x over n, where x is the observed successes in n number of trials. Now, you may have heard that saying in the past, mind your P's and Q's. Kind of think about it here. If we've got P, we're also going to have Q. Now, P plus Q is going to equal 1. So if we know what P is, we can figure out what Q is by going 1 minus P. So this is that formula that I talked about on the last slide, but I wanted to put it here officially as well. The sample proportion, or p hat, is computed by taking x, or the number, which is the number of members in the sample that have a specified attribute, or the number of successes, and as usual over n, which denotes the sample size. So this is how you calculate your p hat. So to make inferences about a population mean mu, we must know the sampling distribution of the sample mean, and that is the distribution of the variable. Now we have to do this for every time that we go through some sort of an inference, and it's going to be the same for our proportions. To make inferences about population proportions, which is p, we need to know the sampling distribution of the sample proportion, which is the distribution of the variable. So this is the theoretical setup to make sure that we know and understand how to make our inferences. Okay, so let's talk about the sampling distribution of the sample proportion. And remember, this is all just theoretical to get us set up so that we can do the inferences. So for sample size, or samples of size n, the mean of p hat equals the population proportion. So mu p hat is equal to p. The sample proportion is an unbiased estimator of the population proportion. This is just a fact. The standard deviation of p hat equals the square root of the product of the population proportion and 1 minus the population proportion divided by the sample size. So this is the square root of p, and then q, so 1 minus p is q, pq, divided by n. And p hat is approximately normally distributed for a large n. Now, when you're using p, you're going to have proportions, so there are going to be numbers between 0 and 1. So a really close approximation, if you have p of 0.5, 1 minus 0.5 is what? It's 0.5. And so this one ends up being the most accurate. So let's set up the simulation for it to prove that this fact is plausible. So playing hooky from work. Now this is the example we're going to use through all of this. So suppose that 19.1% of all US employees play hooky. That is that the population proportion P is equal to 0.191. So where did I get the 0.191? It comes from this percentage and we turn it into a proportion. Okay, so P is equal to 0.191. Now I want you to stop. If P is equal to this, what is Q? Q is going to be equal to 1 minus 0.191. So then according to our key fact from the last slide, for samples of size 1010, the variable p hat is approximately normally distributed with a mean of mu p hat equaling p. So that's equal to 0.191, and then we can calculate our standard deviation. So how do I know this part right here? Because of the key fact. It is a fact. It's just going to equal that. And the standard deviation is going to equal p times 1 minus p over n, square root your answer. So if we have 0.191 multiplied by 1 minus 0.191 over n, which is 1010, take the square root, then we get 0.012 for our standard deviation. What they did then is they simulated 2,000 samples of US employees, and then for each of those 2,000 samples, they found the sample proportion of those who would play hooky, and they put it into this output here, and it shows a histogram of those 2,000 values of 1010 US employees each, and it was shaped like the superimposed normal curve with the parameters of 0.191 to 0.012. So that means it's centered on 0.191 as its average, and the spread is equal to the standard deviation of 0.012 to either side. Now, when I show you guys those simulations, I'm not asking you to actually do anything with it. You just need to understand those key facts so that we can set up the next part of it. You're not going to get a question on a test with a simulation like that. So This leads us to our next method, which is large sample confidence interval for a population proportion, or we can call this method the one proportion Z interval procedure. The one proportion, Z interval procedure can also be known as the one sample Z interval procedure for a population proportion, or you might see it as the one variable proportion interval procedure. So the one proportion Z interval procedure, the purpose here is to find a confidence interval for a population proportion P. We have assumptions, and they are that it's a simple random sample. We always have that assumption, but we have some new ones. The number of successes, which is X, or the number that have the specified attribute, which is X, and the number of failures, which is equal to N minus X, are both 5 or greater. So what you'll do is when you get a question, you'll write out X equals, and if it's 5 or greater, it's good. And then you'll write out N minus X, and if it's 5 or greater, then it's okay. And if it's not, then you can't run this test. Of course, we will find a confidence level of 1 minus alpha using our Z table. So we're going back to the classic table 2, easy to use. And then we've got our confidence interval procedure here. So it will be P hat plus or minus. So it will be minus and plus your Z alpha divided by 2 multiplied by the square root of P hat times 1 minus P hat or Q divided by N. And of course, Z alpha 2 is found in that step 1 for your confidence level, and you have P hat equaling X minus or X divided by N as the sample proportion. So we need to talk about that second assumption again. So a condition for using the procedure is that the number of successes and the number of failures are 5 or greater. And we can restate this condition as X and N minus X are both 5 or greater, and we don't know that often for P, and we'll have to figure that out. All right, gang, let's do an example. So playing hooky from work. A poll was taken of 1010 US employees. I'm going to stop right there, and you guys should too. And you should write down N equals 1010. The employees sampled were asked whether they play hooky, that is, call in sick at least once a year when they simply need time to relax. 202 responded yes. Okay, let's stop right there. We should write down 202. But what does this indicate? What is 202? It is the number of people who have the specified attribute or the number of successes. So we're going to stop. We're going to write X equals 202. Use these data to find a 95% confidence interval for the proportion P of all US employees who play hooky. Okay, so at this point you should have N, you should have X, and we're going to go back and think about our assumptions. It's a simple random sample because it is. We're just going to say, yes, it is one, we know because it says in the question. But what are the other assumptions? Well, N and N minus X both need to be 5 or greater. So you'll want to stop and you'll want to do that right now to make sure that you meet that assumption. Okay, so now that you've done that, use these data to find the 95% confidence interval. Okay, you guys should be getting really good at these. And like I said in the beginning, sometimes you're going to just start to memorize this stuff, right? So if it's a 95% confidence interval, then we know it's alpha divided by 1 minus, right, 0.95 is equal to 0.05. That's where I got that. You always go 1 minus alpha, so 1 minus 0.95 is equal to 0.05. 0.05 divided by 2 is equal to 0.025. Now, this is skipping that step where you go 1 minus 0.025, you get a number, you look in the body of your table to go back to find 1.96. So you guys should be okay at doing this stuff by now, but if you are confused, you need to stop, you need to go back, you need to practice it again. I was talking to some other students that I teach, and a lot of them were telling me that, and I'm not teaching them statistics right now, but a lot of them are telling me that they're feeling kind of confused about this portion here, and that's totally normal. It happens. What happens is you think you get it down and then you kind of forget about it. So just keep practicing on these and you will be fine. Okay, and then the confidence interval for P is from, and this is just the formula here. Now, before I show all of the answers for it, though, I want you guys to take a step back. What is P hat? P hat, write P hat up here and write out what the equation is. You need to find all of this stuff before you go forward, with the actual equation. So P hat, right, I'm going to write it here, is equal to, my hat's really narrow, it's equal to x, so 1010 over, or sorry, that's 202 over n. So it's going to be equal to 202 divided by 1010. So let's try and plug those in, though. You can try and plug all of these numbers in that you have and see if you can get the right answer. Okay, and here is the answer if you didn't do it. So you can see here that they're showing how they calculated the p hat, which is equal to x over n, which is 202 divided by 1010, and we get 0.2. So 0.2 is our p hat minus z alpha, which is 1.96, multiplied by the square root of 0.2, 1 minus 0.2, divided by 1010. And then what you get for your answer here is 0.175 to 0.225. But some of you guys are missing your interpretation. So how would we interpret this? We can be 95% confident that the percentage of all U.S. employees who play hooky is somewhere between 17.5 and 22.5%. So when you interpret this into a percentage, it helps put it into context. We've talked about the margin of error in estimating an unknown population mean by a sample mean in past lectures. But in general, the margin of error of a point estimate, what it does is it will indicate the accuracy with which it estimates the value of the unknown parameter in question. And so most confidence intervals that we encounter have endpoints of this kind of a form. So for the one proportion Z interval procedure, the point estimate here is our sample proportion. And we can see the margin of error formula here, denoted with the letter E, is equal to our Z alpha divided by 2 multiplied by that square root of P hat times Q divided by N. So what if we wanted to figure out how big a sample size we need to estimate a population proportion? So like the percent of people who agree with something. And we want to do that with a certain amount of accuracy. So the key idea here is that the sample size will depend on your confidence level, or how confident you are or want to be, and how precise you want to be, which would then be your margin of error, and how the variable or how variable the proportion is based on your P. So you've got a couple of cases. Say you have no idea what your proportion is, because often we will be given things like the margin of error and we'll be given things like the Z alpha, but we don't actually know P hat. So if you don't have any idea what P hat is, then you use this formula right here, where n equals 0.25 multiplied by Z alpha divided by 2 over your margin of error squared. And we use this formula because it's a safe formula. We use 0.25 because the variability is largest when your P is equal to 0.5. So this gives you the largest or safest sample size. But there's another case. You can guess, make an educated guess on what your P hat is. And that's when you would use this formula here. And you can see that they denoted it P hat G for guess. So this is usually a smaller and more efficient because it uses any prior knowledge that you have. So there's a kind of an important tip here. If you think that P hat is in a range of like 0.3 to 0.4, use the value closest to 0.5. This keeps your sample size from being too small. You want to make it conservative. So in very plain sort of language here, Smaller margin of error, or E, a bigger sample size is needed. Higher confidence, bigger sample size is needed. More uncertainty, or the closer you are to 0.5, the bigger sample size you need. So you're choosing a sample size big enough to get the precision and confidence that you want. And if you're not sure, assume the worst case scenario, the 0.5, to be safe. Now, if the margin of error and confidence level are specified in advance, then you can go ahead and you can determine your sample size to meet those specifications. Okay, and so let's just do a quick example here. We're going to look at A and B. Consider again the problem of estimating the proportion of U.S. employees who play hooky. Obtain a sample size that will ensure a margin of error of at most 0.01. So right away you should stop. You are looking for an N, and you know E is going to be 0.01, and you have a 95% confidence interval. So you know you're looking for N, and that will lead you right to this formula here. So in this one, we don't have our P hat, so we're going to use the 0.25, and we're going to take it over the 1.96. I got that because it's a 95% confidence interval, and take it over the margin of error. And then we can interpret that based on a sample of 9,604 US employees, we can be 95% confident that the percentage of all US employees who play hooky will be somewhere between 18.6% and 20.2%. And that's down here in B, where we actually do the confidence interval here. Now we're going to look at hypothesis tests for one population proportion. And we call this hypothesis testing procedure the one proportion Z test. It will also be called the one sample Z test for a population proportion, or the one variable proportion test. And I've got the formula here on the screen. This is the formula that we're going to be working for. Here is the procedure for the one proportion Z test. So the purpose is to perform a hypothesis test for a population proportion P. Our assumptions here is that it's a simple random sample, and both N, P sub O, and N times 1 minus P sub O are 5 or greater. So that's going to lead us into a little bit of a discussion about what is P sub O here. We'll get there though, we'll cross that bridge when we get there. So let's start with step 1. The null hypothesis is always going to be HO, P is equal to P sub 0. And the alternative hypothesis will either be two-tailed, left-tailed, or right-tailed. We're always going to decide on our significance level and compute the value of our test statistic. Now, once we're done all of that, we have to make our decision using the critical value approach or the p-value approach, and this hasn't changed. This is going to be exactly the same. So, what is p sub 0? Let's look at an example. Okay, let's do an example. Economic powerhouse. In early February 2013, Gallup conducted a national poll of 1,015 U.S. adults who asked which country is the leading economic power in the world. So, stop and write down your N. Of those sampled, 538 said China. This is your X. This is the number of people that have the attribute. At the 5% significance level, do the data provide sufficient evidence to conclude that, at the time, a majority, more than 50%, of the U.S. adults considered China the leading economic power in the world? So now you have N of 1015. You also know X is 538. I don't have that written down, but I really should. And then we've got P sub O. P sub O is your population. So it is 0.50 or 50%, whereas your P hat is your sample, right? So this is the sample, this is the population. What is P hat? P hat is equal to X over N. So 538 divided by 1015 is equal to 0.530 minus your 0.50, which is the population proportion. And then we've got to go through our assumptions, right? So we've got N, we know what P hat is and how we get it. We know what P sub 0 is and how we got it. Now we have to look at these two assumptions here. N times P sub 0 and n times 1 minus p sub 0 or your q need to be 5 or greater. And so you just have to quickly do that little calculation and you'll see that they're both 5 or greater. Now, of course, they're the same number. And how is that possible? Because it's 50-50, right? So it equals 1. All right, so our null hypothesis here is that p is equal to 0.50 or that your p is greater than 0.50 or a majority consider China the top. So all you have to do is kind of pop in your numbers in here and you should and make sure you get a z stat of 1.91. Once we have that Z stat, we now need to make a decision. And we're going to use the critical of value approach here. We have a 5% significance level, and so we know that that equals the critical value of 1.645. And if you look at this number line and you plotted 1.91 on the number line, it would be back in here somewhere. So we would reject our HO. At the 5% significance level, the data provides sufficient evidence to conclude that a majority of U.S. adults consider China the leading economic power in the world. You can also use the p-value approach here, and if you do so, you'll find that it falls somewhere between 0.01 and 0.05, and on technology, the p-value is actually 0.02, which is far less than our stated value of 0.05. Okay, so we've looked at inferences for one population proportion, and now we need to look at it for comparing two populations and proportions. So in this case, what we'll have is two populations, one specified attribute, and the problem is to compare the proportion of one population that has that attribute to the proportion of the other population that has that attribute. And this section gets a little bit messy with all of the notation. So I put this chart in here just for you guys to keep it in mind. This is the notation for parameters and statistics when two population proportions are considered. So your population proportion is P. And remember, your sample proportion is P hat. And of course, the first population will be denoted with a 1 and the second with a 2, and so on from there. So you've got your sample size is N, number of successes is X, and then you've got your p hats, all 1 and then all 2. And to calculate your p hats, because now you'll have 2 of them, you take the number of successes and you put it over the population. So the number of successes equals the number of members sampled that have the specified attribute. And now that you guys have kind of reviewed the notation and you might be feeling more comfortable about the ones and the twos, we can look at this key fact here and we can talk about sampling distributions for the difference between the sample proportions. So for independent samples of size N1 and N2 from two populations, mu p hat 1 minus p hat 2 is equal to p1 minus p2. That means that the difference between sample proportions is an unbiased estimator of the difference between population proportions. And then you can get your standard deviation, which is equal to the square root of p1 times q over n1, p2 times q2 over n2. And p hat 1 minus p hat 2 is approximately normally distributed for a large n1 and n2. So keep in mind that this is the theory stuff that we need to bring up to set you up for moving on to actually doing the different types of inferences. Okay, so we're going to look at the hypothesis test procedure for the differences between proportions using two independent samples. And you can't really see it, but it says the two proportions Z test down here. So the purpose of the two proportion Z test is to perform a hypothesis test to compare two population proportions, P1 and P2. Our assumptions here is that it's a simple random sample, it's an independent sample, but look at number 3. We've got a few more things we've got to test for. So x1, n1 minus x1, x2, and n2 minus x2 are all 5 or greater. And it's really simple to do that, right? You just look at it. The null hypothesis here, H sub O is P1 is equal to P2, and then your alternatives are two-tailed, left-tailed, or right-tailed. Now we'll decide on our significance level of alpha, and we can compute the value of the test statistic down here. But we need to take a stop because check this out right here. We need to calculate something called P hat sub P, and that's equal to x1 plus x2 divided by n1 plus n2. So you almost have to do this here, up here. So I always take this kind of thing and I write it up in here. And we'll talk about what this means and what it is as when we do the example. So once you get your value of z, then you'll just go through the same approach as either the critical value approach or the p-value approach to decide if you will reject or fail to reject your, or not fail to reject your hypothesis. Okay, so let's talk about this P hat sub P, and this is the pooled sample proportion. So we have to estimate P by using sample information, and the best estimate of P is obtained by pooling the data to get the proportion of successes in both samples combined together. And it's really easy to calculate it, and you could write this down on your formula card if it's not there. What you'll take is x1 plus x2 divided by n1 plus n2, and you pop that in right here and right here. And then you can use that in your procedure to get a little bit better of an estimate. So here it is again. I wanted to show you another way with it all together. So the test statistic for the difference between two proportions when your population proportions are unknown, what you'll have is p hat 1 minus p hat 2 divided by the square root of your pooled probability or your pooled estimate. And again, this is x1 plus x2 divided by n1 plus n2. And then you go through with the rest of the equation. The pooled probability is p sub p or p hat sub p and is the total number of successes divided by the total number of observations with the two samples combined. And of course we do this because it gives us our best estimate of p. This is a pooled probability, and this is similar to like a pooled standard deviation, which you guys have done in the past. So let's do the example, eating out vegetarian. So this company surveyed 1,181 US adults to gauge the demand for vegetarian meals in restaurants. The study commissioned by the Vegetarian Resource Group and published in the Vegetarian Journal, I don't know if that's real, polled independent random samples of 747 men, so stop, N1, 747, and 434 women. Stop, N2 is equal to 434. Of those sampled, 276 men and 195 women said that they sometimes order a dish without meat, fish, or fowl when they eat or eat a vegetarian dish. So the 276 and the 195 are your X's because that's the success. That's the ones that are saying, yes, we have this attribute. So you're going to want to stop and you're going to want to write that down, right? So as you're going through the equation, write down what you know. So let P1 and P2 denote the proportions of all US men and all US women who sometimes order vegetarian respectively. And so our null hypothesis will be that the percentage for men is not less than that for women, or they're equal to each other. P1 is equal to P2. And the alternative hypothesis for this is that the percentage for men is less than that for women. And so we've got P1, and that is going to be less than P2. So the test you need to perform here at the 5% significance level, or at an alpha of 0.05 here, is written right down here. So I just want to take it back a step because I think I just kind of skipped over something. How do I know that we're doing this left-tailed test? Because the question's really asking us, do the data provide sufficient evidence to conclude that the percentage of men who sometimes order veg is smaller than the percentage of women? And that's where I got this from. And we're going to use that 5% level of significance. So you can calculate your p hats, right, which is x1 over n1. So look where these numbers came from, 276, 747. And then you can do your x2 over n2, 195 over 434. And while you're going through this, you can start to think about the assumptions as well. And this will meet all of those assumptions. And then you have to calculate your p hat p, or your pooled probability, and that's equal to x1 plus x2 divided by n1 plus n2. And you can see that here, x1, x2, n1, n2, all over here. And that equals 471 over 1,181. And so you get a p hat p of 0.399. So all you have to do is put all of the numbers in here and calculate it. Make sure that you do it and get this answer. And I find that people will freak out when they get a negative number. It's totally fine to get a negative number, and it's left-tailed, so you would expect it. So now we have this z value of negative 2.71, and we have to make a decision. So use the critical value approach, because it seems like you guys like that one better. And with the critical value, for a left-tailed test is a negative Z alpha. We know that the critical value that we're going to use for 5% is always 1.645, but since it's left-tailed, we're just going to put a negative in front of it. It's going to be negative 1.645. So is the 2.71 falling within the rejection region or not? And it actually does fall in the rejection region. And so the test results are statistically significant. At the 5% significance level, the data provides sufficient evidence to conclude that in the US, the percentage of men who sometimes order veg is smaller than the percentage of women who sometimes order veg. And as always, there's a confidence interval procedure that goes with this. It's the confidence interval procedure for the difference between two proportions, or the two proportions Z interval procedure. The purpose of the two proportions Z interval procedure is to find a confidence interval for the difference between the two population proportions, P1 and P2. Now our assumptions here are that it's a simple random sample, they're independent samples, and that x1, n1 minus x1, x2, and n2 minus x2 are all 5 or greater. And we're going to use our Z table, or table 2, for our confidence level of 1 minus alpha to find our Z alpha divided by 2. And the endpoints of the confidence interval are going to be equal to p hat 1 minus p hat 2 plus or minus. So you'll do this twice, once subtracting, once adding. Z alpha divided by 2, the square times the square root of p hat 1 q1 divided by n1, p hat 2 times q2 divided by n2. I've also written it out here just so that you can see it really large, and hopefully you can use this to copy. It can be really hard to find that p hat symbol, so if you have to write out just p hat like you do with some of the other things, I'm totally fine with that. And even though it can get kind of boring just doing hypothesis tests and confidence intervals, one thing that's really nice about doing them is that usually once you do the hypothesis test or the confidence interval, you'll have all the information you need to do the other one. So let's do the confidence interval for our same example on eating out vegetarian. And this one here is saying to find a 90% confidence interval for the difference P1 minus P2 between the proportions of US men and US women who sometimes order vegetarian. So I've written out along the side our x1, our x2, n1, n2. And our first step is to find the confidence level 1 minus alpha. So this was a 90% confidence interval, so we have an alpha of 0.10. If we take 0.10 divided by 2, we get Z 0.05, and that of course equals 1.645. Now, as I said that or spoke through that, I did skip a step. So if you're not sure where I got that 1.645, you need to go back and make sure you know. All right, now all you have to do is really take the values that you have and put them in here, right? So p hat 1 minus p hat 2, and of course these are equal to x over n, and you calculated that before. So p hat 1 is 0.369, n1 is 747, and so on. Put all of those in there, and you should do this twice, once adding it, once subtracting it, and then you will get these numbers down in here. And then remember your interpretation. We can be 90% confident that in the United States, the difference between the proportions of men and women who sometimes order vegetarian is somewhere between 3.1 and 12.9 percentage points. So we've got the negative 0.129 and the negative 0.031, and those will equate to percentages of our 3.1% and 12.9%.